we are once again at the physics video lecture. It is Psci 168 video lecture 17. So we're in the middle of the hydropower project, a major part of this whole semester. I'm going to do some review and then discuss different types of dams, and this time I will stop a little early because I want you guys out there finding lots of images. So let's begin. Once again, hydropower. We'll start with our cartoon that I like to draw and label. We've got the lake. We're just going to keep adding to this thing. We have the lake being held back by the dam. And so there's a mass of water up here. What makes this mass of water a form of stored energy is that it is located above something. Now there are a couple of interesting details here. If the mass of water, or if the power plant is just at the base of the dam, then that height that we have that we're about to put in our formula isn't that necessarily that high, but the power plant can be located way down at the foot of the mountain. So there are different possibilities there. I'm going to do this foot of the mountain version. So let's smooth out that surface a bit. Okay. So we've got the water. There's some connection called a penstock to a powerhouse down here. And then there is an outflow with a lower level of water, and it's actually the difference in height between these two levels of water that measures the energy stored in the dam. If we're talking about the energy, complete energy stored in the dam, we could actually say that we have to take the midpoint of that water there, but that's a detail we're not too worried about. We'll go ahead and go from the top surface down to the bottom. Okay, so how much energy is there? Once again, we'll use the letter capital W. It's just the mass times G times H. Okay. And that mass can be written density of water times volume. I'll put parentheses around it. So when you actually calculate it, this number never changes. That's 1,000 kilograms per cubic meter. This volume depends on the size of your reservoir. So that's what we learned to do last time. I'll say or work rho GH. Put it in a red box. Good. And what we had learned last time was also, and remember, always kilograms, meters, and seconds. So everything is in terms of our basic quantities. That way our formulas always come out right. So the units are going to be joules. But then we learned that we can express joules in terms of kilowatt hours, and we haven't talked about any kind of electricity yet, but that's just a physical quantity. Eventually we'll learn how to get the energy, out to the rest of civilization. But nonetheless, the kilowatt hour quantity is interesting to us because we pay our energy bills in kilowatt hours. So that conversion was so I'll just write here, joules can be converted to kilowatt hours. Kilowatt hours. And the conversion is this. 1 kilowatt hour, which is 1,000 watts times 1 hour, converted to joules and seconds, it turns into 3.6 converted to joules, okay? 3.6 times 10 to the 6 joules. So that is a conversion factor that you can always use. Yeah, so that's what we learned last time. And this time, I want to talk about dams, okay? And give you a list of different types of dams. I'll say a couple words about their construction principles, but what I want you guys to do is go look for good images for your book. And if you're anything like me, then you'll probably learn a lot just in the search, because you always find interesting stuff that you weren't looking for. Good. So what about these different types of dams? So I have a list here that just one is the earthen dam, and that's really holding back the water with a very, very large wall of earth and stone and what have you. Okay, so that type, actually, you do not want water overflowing on something like this. Y'all mentioned dam catastrophes while we're at it, but you've got the earthen dam, so you want to get images of all of these. Images, and whatever you print out, make sure you label it as to what it is and possibly where it is and how big it is and so forth. Another type of dam is a gravity dam. And that one's interesting in that the principles of statics are something along the lines of what we've talked about this semester. So suppose you're holding back a lot of water, okay, and you've got your so-called gravity dam. The idea here is that this is say, a concrete wall of sufficient depth to actually resist being tipped over simply by the fact of its size, okay? So that's why I've drawn it with a longer foot here, okay? This thing resists the water up here just because of its immense size, but this is, say, a concrete structure, and the pressure, you know, the force on this dam, if you imagine it, you know, the average force acting in the center, right, it would be acting in that direction. And if the base is wide enough and it's massive enough, it can hold the water back just by virtue of its bulk and shape there. So there's your gravity dam, holding back the water. And again, images. So our next type is going to be the arch type, and we studied arches, and so these are kind of fun to look into. So the next ones you're going to want to look up arch dams, and I'm going to give a top view, because from the side, well, I'll do both. So from the side, kind of a profile here, they have this arch shape, and they're often across a narrower canyon, and the water is back here, okay? The top view, and here's something you want to get some images of. The top view, say you had, so we're looking down on it. In fact, Hoover Dam, you'll find some really nice aerial views of this type. You'll have the water back here, okay? It's not streaming, I'm just drawing the water. So if you do a top view of an arch dam, it's going to look like this, okay? And here are the canyon walls somehow. You're looking down, say, a satellite view. And what's nice about the arch dam, if you've studied the arches the way we have, you recognize the arch principle. That's why this is the upstream side of the dam. You recognize the principle of the forces being pushed tangentially and into the side of the canyon here. So let me recommend that you find some nice arch dam pictures. This is the top view. I'm thinking of a Hoover Dam picture that I would have shown you if we were together here, but I think it's going to be much better for you guys to find them. So example, very good example, Hoover Dam. That's just to get you started. As you look around, you'll find all manner of good examples of these. So that's the aerial view. And it's this beautifully curved shell often. Okay, you'll see the shape of it takes on a certain beauty just because it's that curved shape that we learned about, for example, with the catenary. Okay, it's the shape that transmits the forces into tangential forces and try to, push them in the side of the canyon wall. So arch dams are an important kind. Let's see, we have a couple more. A multiple arch dam or buttress dam. So also referred to buttress dam. An example is our very own Florence Lake up here in the Sierra Nevada. But that's not the most impressive example, but it's local. For Florence Lake. Now, the best thing to do with a multiple arch dam is to try to draw a top view, because the thing is, the arch dam you tend to want to have on a narrow canyon. What if you don't have a narrow canyon, right? These gravity and earthen dams are very, very wide often. Well, what can be done is multiple arches. So you have these arches here. Let's just draw a series of them. Now I'm drawing the top view. So here's a series of arches for a high dam, and of course it would be pushed over if you were looking from the side. You have these little shells here. It would be pushed over, except that there's a buttress, but it's a narrow buttress that's put right here. So there are then these narrow buttresses that jut out. Again, this is the top view, and the water is up here. Here's the reason I want you guys to get images, okay? Because you'll see, so top view. Yeah, this picture isn't really doing it, but you guys are going to go find some, okay? And in fact, there are some very beautiful multiple arch or buttress dams that I think you'll enjoy seeing. And I think you'll see the principle. Give it another attempt here. I try to do a better one than. Actually, now that I look at it, that picture up there isn't that bad. Let's see if we can. Continue that. So the profile view, you've got a multiplicity of these kinds of arches. Okay. Now, there would be another one here. Okay. These would be your arches. And of course, these big, tall, arched shells don't have the intrinsic strength, but if you put a buttress on each one, and it could just be a narrow buttress, that will do the trick. is actually a little better. So yeah, look these up. This is the reason I want you guys to get good pictures. So the multiple arch dam, definitely an interesting one. And yeah, so you see the construction principles and you see our discussion of forces. Forces, the vector nature of force, the arches come back to haunt us, but actually it's come back as an application of some of the stuff we've learned. So yeah, that's a major assignment in terms of getting some good images for your book, for your notes, and being able to understand them as well. So by the time you print something out and put it in your book, I want you to analyze it a bit and really understand what the picture's showing. Good. And what is that all for? It's for holding water back, like our original picture, above a valley. Now I have a couple of interesting things as well, because if you look up this kind of material, you may run into some dam disasters. So that was 4. This is just a side note. Disasters. There are some famous ones, and they're always possible when you have a large amount of water here. So once more, we've got our dam here. You've got a large amount of water stored. These are enormous masses of water. And so there are a couple I'd like for you to look up. One of them is the Teton Dam. Go ahead and put in Teton Dam. You're immediately going to see that it was of the earthen dam type, and there's actual footage of the dam break. And there was another interesting one. I have the name there. Hope I wrote this down right. So Teton Dam, V-A-J-O-N-T. This was Italy. I think 1963. This one is interesting because it was a very, very bold arch dam in a narrow canyon, and it was not a dam failure. Teton Dam actually burst. The Vajont Dam suffered a landslide behind it, and a gigantic wave, if you have a landslide behind the dam, it threw a gigantic wave over the dam. The dam itself stayed and exists to this day, but it was a gigantic wipeout of entire cities downstream. So yeah, look up that, and you can find other ones as well. They're interesting because you can see some of these forces in action and what we're up against when we're trying to hold back large masses of water. Okay, I'm going to consult the clock here. This was supposed to be a short one, but I can't resist telling you guys a little more. So this is the major project of this hour here, is for you guys to go out and find some good images and learn something about all these things. What I'll do next is talk about the hydropower power formula, and we'll just get a start on that, and then we'll continue with that next time. A lot of these topics are good. They don't suffer for the repetition because you have to see it a few times in order to feel comfortable with it. Okay, good. So what do we have? We're going to draw our dam one more time, and the penstock and everything, and we'll talk about the actual power formula. So there's our water. And here is the penstock. So I'm just relabeling or redrawing. And here's the lower water level. Okay. And this is the height H. Okay. Between those two water levels. So now we know what happens is we have to take water. The reason it has energy is, of course, because it's elevated here. But we're going to get the power formula in the following way. So this is power formula. First of all, remember what is power. Units of power are watts, which is joules per second. So units, joules per second equals watts. Okay. We want to know how many watts of power we can get out of this powerhouse here due to this water running down. Okay. So what we do is we take, right, it's energy per time. So i.e. power equals work per time. So we already know the numerator. What I'm going to do is this. P equals mgh, which was the energy, divided by T. But I'm going to just set some parentheses here. This is, remember, the same formula we had for the stair climb, and essentially also for the grandfather clock. So it's nothing new, but what's new is the way we set the parentheses. It's m over t times g times h. So what does that mean? All we have to do is speak what we're looking at here. We have mass per time times g times h. We already know about g and h. So what about mass per time? That's kilograms per second of water. Kilograms per second of water that is flowing. So this is called the flow rate in kilograms per second. Flow rate in kilograms per second. And I'm not going to make a new name for it or a new letter. We'll always just say m over t with parentheses around it. But the units are the same. These are watts, and if we, G is approximately 10, H is however much we can manage in our construction, then the power is simply going to be the flow rate in kilograms per second times G times H. I'm going to end with an example of some really simple numbers. And yeah, let's have a look. So my example is going to be a medium amount of energy. We've used this formula with the grandfather clock, and it was a tiny wattage. We used it for our stair climb, and it was 500 watts, maybe 1,000 watts, right? If you're a football player. And we're now going to use it for a hydropower scenario. So the example is the following. Let H be 100 meters. That's a nice size drop. But we had a 500 meter drop in our other example, and they can be higher, they can be lower. Okay. So let H be 100 meters. We're going to just take G 10 meters per second squared. We don't need a calculator here. And let the flow rate and 1 cubic meter of water per second. we can imagine a pipe that's running a cubic meter of water per second. Cubic meter is this enormous cube, right? And for a hydropower project, that's not very much, but for a backyard project, of course, that would be a lot. So a cubic meter of water per second, but we know that is 1,000 kilograms of water per second, because the mass in a cubic meter, we learned last time, was 1,000 kilograms. So we have M over T, our flow rate, is equal to 1,000 kilograms per second. So what do we have? These three quantities, and we'll just put them together. The resulting power, result, is P equals, and I'm just using that formula there, so it's 1,000 kilograms per second, 10 meters per second squared. That's G in 100 meters. So you notice I chose some great numbers here, okay? That's 10 to the third power, times 10 is 10 to the fourth, 2 more zeros is 10 to the sixth, okay? So this power here is 10 to the sixth watts, and of course 10 to the sixth is 1 million, okay? And I'll just give you some, so equals 1 million watts. And that happens to be referred to with its own name. It's called a megawatt. Equals 1 megawatt. Megawatt. You know, for us, powers of 10 are really the way to go. Okay. But you'll hear the word mega often enough, it means a million. Okay, so megawatt is 1,000,000 watts. Well, how much is that? That's a lot more than your refrigerator uses, but it's a lot less than a whole city uses, okay? So a megawatt is a decent unit of power if you're talking about larger scale applications. One of these dams, a larger dam, as we'll keep studying them, will deliver 1,000 megawatts or more, can deliver that much. So 1,000 times this much is what we're using to run our civilization. And as individuals, we use, 1,000 watts, maybe a kilowatt at a time, maybe even more sometimes. Okay, but those are the related, the relative quantities. Good. I think this is where we're going to leave it. We're gonna, you guys are gonna go out, get all your pictures of the dams, understand them as best you can. This got us started on the power discussion, and what we'll do next time is some more examples of this, and then we'll continue to analyze this scenario here. What we're going to start doing is adding, snow-covered mountains behind it, and power plants and transmission lines and other stuff like that. As we find all the other aspects that come into play here. Right now, we're just very basic. We know there's energy stored between higher and lower point, and we know how to calculate that energy, and now we know how to calculate the power. Good. See you guys next time.